Imagine for a second that you are burning literal tons of coal every single day. I mean, just shoveling it into an enormous industrial furnace, watching the flames roar. And all of this effort, all of this combustion, is entirely for the sole purpose of heating a massive volume of water up to 200 degrees Celsius.
Right. A massive amount of energy.
Exactly. You spend incredible amounts of capital on this fuel, on the heavy infrastructure, on the labor to keep the fires fed, the logistics of just moving that coal into your facility.
Oh, yeah. The supply chain alone is a nightmare.
Yeah. And then, once that water finally reaches that perfect blistering temperature, you open a heavy iron valve and take a massive pipe and you just dump it straight down the drain into the sewer.
It sounds completely absurd when you phrase it like that.
It really does. But, have you ever thought about the hidden leaks in our industrial world? Like the places where massive amounts of energy and money just quietly slip away while everyone assumes the system is working perfectly?
It is a phenomenal image to start with, honestly. And what is so striking about the scenario is that it isn't some hypothetical thought experiment, right? Or like an exaggerated worst-case scenario.
Right, you're saying this actually happens.
Oh, absolutely. This is the daily, hour-by-hour reality in tens of thousands of industrial facilities across the globe right now.
Wow.
Yeah, it happens so routinely, so quietly, that it has basically become practically invisible to the people running these plants. I mean, we look at towering smokestacks and think about combustion efficiency, or we look at supply chains and think about logistics.
Sure. The big visible stuff.
Exactly. But we very rarely look down at the floor drains. And the drains are where the real structural hemorrhaging happens.
And that hidden hemorrhaging is exactly what our mission is for this deep dive. Welcome in, everyone. We are going to uncover a specific, incredibly obscure industrial choke point known as boiler blowdown.
A very niche term, but hugely important.
Right. But we aren't just going to point at a leaking pipe and move on. We are going to break down the specific mechanical engineering principles behind the solution, specifically the Aegis TDS loop automation strategy.
Yes, the Aegis strategy is fascinating.
It really is. We've got a dense and really fascinating stack of sources for you today. We are pulling from heavy-duty engineering handbooks, from Veolia and Forbes Marshall. We're also looking at granular, highly technical boiler audits taken straight from the textile industry.
Real-world data.
Right, real-world data. And we are unpacking these highly strategic, almost philosophical operational blueprints of the Aegis strategy itself.
The cross-section of documents we're looking at today bridges several entirely different worlds.
Completely.
Like, we have the raw, unforgiving thermodynamics of thermal waste on one hand. Then we transition into the exact mathematical formulas and the physical control logic needed to fix that waste.
Which is heavy on the math, but we'll break it down.
Right. And from there, we get into the psychological and operational mindset required to deploy that fix into a dangerous environment. And finally, we look at the financial models.
The actual business structure.
Exactly. The economics that make this kind of restorative engineering an absolute necessity for facility managers.
So we obviously have a lot of ground to cover. I want to start by setting the stage with just the sheer physics of the problem.
Good place to start.
For you listening, if you've never stood inside an industrial plant, we need to understand what actually happens inside an industrial steam boiler. Why are we dumping this boiling water down the drain in the first place? I mean, intuitively, if you spend money to heat water, you should want to keep it.
Right, you'd think so. But to understand the intentional waste, you have to understand the core function and the vulnerability of the machine itself.
Oh, lay it out for us.
So an industrial boiler's entire job is to turn liquid water into steam, right? Which is then used to power turbines, heat vats of dye in a textile plant, or sterilize equipment.
Standard industrial stuff.
Exactly. But here is the critical mechanical truth that sets up our whole problem. Steam is essentially pure distilled water.
Okay.
When liquid water evaporates into a gas, it leaves practically all of its dissolved minerals behind in the liquid that remains sloshing around in the bottom of the boiler drum.
So we're talking about total dissolved solids, TDS. In the sources, they list minerals like calcium, magnesium, and silica.
Yeah, those are the primary culprits. Now, industrial facilities don't just pump raw river water into a boiler, right? They have water pretreatment programs, softeners, reverse osmosis systems, but no system is 100% perfect.
There's always some trace amounts left over.
Right. The feed water, which is the water constantly being pumped into the boiler to replace the water that boiled off into steam, still contains a trace amount of these dissolved solids.
Makes sense.
So as the boiler operates, it is constantly boiling off pure steam and taking in fresh makeup water. And because the minerals don't leave with the steam, their concentration in that remaining pool of boiling water continuously spikes.
Ah, I see. So if we leave this unchecked, those dissolved solids eventually reach a saturation point. They precipitate out of the water and form a physical crust, like they form scale.
Precisely. And scale is the ultimate nemesis of thermal engineering.
The nemesis, that's a strong word.
It really is.
Yeah.
When we review the Forbes Marshall Engineering Handbook, the data on scale is alarming because scale has a terrible thermal conductivity profile compared to bare carbon steel.
Okay, so it blocks heat.
Right. The steel tubes in a boiler are designed to transfer the immense heat from the furnace fire directly into the water. Scale acts as a highly effective, incredibly destructive thermal insulator, blocking that transfer. Okay, let me stop you there, because the Forbes Marshall source had a specific metric that I couldn't quite believe.
The 1 millimeter stat.
Yes. They point out that even a microscopic 1 millimeter of scale buildup, which is literally the thickness of a standard plastic credit card, can reduce heat transfer efficiency by up to 10%.
It's staggering.
10%, just from a millimeter of buildup. How does something that thin block that much heat?
Well, it comes down to the density and the molecular structure of those specific minerals. Calcium carbonate and silica are essentially rock.
Literally rock.
Yeah, literally. You are lining the inside of your heat transfer equipment with stone. The consequences of that 1 millimeter layer are twofold, and they compound each other.
Okay, what's the first consequence?
First, your fuel wastage skyrockets. The furnace now has to burn significantly more coal just to push the necessary heat through that new insulating layer of rock to reach the water.
Because it's fighting the insulation.
Exactly. The data shows fuel wastage increases anywhere from 2 to 5% instantly.
Which is already a financial nightmare if you're buying tons of coal.
Yeah.
But the second consequence is the physical danger to the equipment, right?
Yeah. Oh, the physical danger is catastrophic. Because the heat from the roaring furnace can't transfer efficiently through the scale and into the water, the heat has nowhere to go.
It just builds up.
Right. It backs up into the metal boiler tubes themselves. The steel begins to overheat beyond its metallurgical design limits. It softens, it warps, and eventually you get tube ruptures.
Wow.
And in the worst case scenario, this localized overheating leads directly to a pressure failure and a massive boiler explosion, which can level an entire building.
Okay, so the stakes are incredibly high. To prevent the boiler from essentially choking itself with rock and turning into a bomb, you have to physically remove those highly concentrated minerals before they can settle and harden.
You absolutely have to.
And that purging process is what the industry calls blowdown. You are deliberately opening a valve to blow the highly concentrated dirty water out of the bottom of the boiler, which makes room to pump in fresh, less concentrated water.
That is the unavoidable mechanical necessity of blowdown. You are actively managing the total dissolved solids.
So it's a necessary evil.
Yes. If you refuse to blow down the boiler, you get scale, you get severe corrosion, and you get a phenomenon called foaming and carryover.
I actually saw that term in the Veolia handbook. Foaming and carryover. What does foaming mean in this context?
Well, when the concentration of solids and impurities gets too high, the surface tension of the boiling water changes. Instead of steam bubbles cleanly breaking the surface and rising as pure gas, the water foams up.
Like a pot of pasta boiling over on a stove.
Exactly like that. That foam, which is full of contaminated liquid water droplets, gets pushed up into the steam lines. It ruins the clean steam supply and can physically damage the downstream valves and turbines. So blowing down the water is completely non-negotiable.
But this brings us to the actual bottleneck, and what I found so fascinating in the Aegis operational blueprints. The root cause of the massive energy waste isn't the chemistry of the minerals, it's the human element.
It's the control point.
Right, the control point.
The intersection of human psychology and industrial hardware is where this problem really lives. Well, for decades, and still today, in countless MSMEs, which are micro, small, and medium enterprises, the primary control point for this critical safety process is a human operator manually turning a heavy, completely uncalibrated bottom blowdown valve.
And because they are doing this manually, they aren't working off real-time data. They're usually operating on an arbitrary shift schedule, right?
Generally schedule-based.
Like the plant manager tells them, open the valve once a shift for 2 minutes, or maybe twice a shift.
Yeah.
But the operator doesn't actually have thermodynamic feedback. They don't know the exact TDS concentration inside that steel drum at that exact second.
No, they are entirely blind to the internal chemistry. They are guessing based on a static set of assumptions.
Is it guessing?
Pretty much. The operator assumes the incoming feed water quality is always exactly the same, and they assume the factory is using steam at a constant rate. But reality is messy.
Right. Things change.
Feed water quality fluctuates constantly based on city supply or weather, and steam loads spike and drop depending on what the factory floor is doing.
So put yourself in the shoes of that boiler operator. What is your primary incentive? Your main goal every single day is to not be the guy on shift when the boiler scales up, overheats, and explodes.
Exactly. Your dominant emotion is a healthy fear of catastrophic failure.
Fear dictates the operational rhythm. When you are managing a high-pressure system blindly, you will always err on the side of caution.
Always.
Let me try an analogy here to see if I have the mechanics of this right. It feels a bit like boiling a pot of salt water on the kitchen stove.
Okay, I'm tracking.
If you keep the burner on high and keep adding cups of fresh water as the steam evaporates, eventually you're just going to have a thick crust of solid salt burned into the bottom of your pot.
Right, the scale.
Right. But in this scenario, you have a heavy steel lid bolted onto the pot so you can't see inside. To make absolutely sure you don't ruin the pot, you just randomly dump half the boiling salt water into the sink every hour and refill it from the tap, just to be safe.
The pot analogy holds up perfectly, but we have to layer in the financial cost of the heat.
Ah, right, the energy cost.
Because every expelled drop of water carrying those dissolved solids also carries a massive amount of paid-for thermal energy. In thermodynamics, we refer to this heat content as enthalpy.
Enthalpy, got it.
You are taking high-pressure water that holds an immense amount of enthalpy and routing it straight to the municipal sewer. When the operator over-purges to play it safe and guarantee no scale forms, they are quietly draining the company's operating budget.
Because they have to replace all that dumped boiling water with cold makeup water from the city line.
Exactly.
Which then forces the furnace to burn a huge pile of extra coal just to bring that new cold water up to the 200-degree operating temperature.
It's a continuous cycle of waste. And this leads us to the analytical challenge. Identifying that a manual operator might be over-purging is only the theoretical half of the battle.
Right, you have to prove it.
Exactly. To actually solve it, to convince a skeptical plant manager to change their operations, you have to mathematically quantify exactly how much money and fuel is going down that drain.
You can't just guess.
No, you can't just walk onto a loud factory floor, point at a valve, and say, I think you're wasting heat. You need to prove it with rigorous formulas.
Let's walk through that proof then, because the mathematical precision required here is intense. According to the sources, you have to execute a rigid 38-hour feed water and makeup water audit to isolate the variable.
A very grueling audit.
What does that audit actually look like in the real world?
Well, it requires a technician physically stepping into the boiler house environment, which is often deafeningly loud, incredibly hot, and thick with coal dust.
Not a pleasant place to work.
Not at all. They have to map the feed water lines and install temporary flow meters. They are taking physical water samples in glass vials every few hours, sometimes at 2 in the morning, just to build a baseline of reality.
2 in the morning? Wow.
Yeah, it's nonstop. They measure the exact total dissolved solids in parts per million at the moment the feed water enters the boiler, and they measure the TDS of the wastewater at the exact moment it exits the blowdown valve.
Okay, so they're trying to find the baseline. Let's look at the specific mathematical formula they use to calculate the absolute optimal blowdown percentage, because this is where the engineering gets highly rigid.
The Thermodynamic formula.
Right, the formula from the Thermodynamic engineering source is optimal blowdown percentage equals the feed water TDS divided by the result of the permissible TDS minus the feed water TDS.
We can ground that formula in their concrete example to show how narrow the margin for error actually is.
Okay, let's do the math.
Let's say the audit reveals your factory's incoming feed water has a TDS of 300 parts per million. And let's say the heavy machinery manufacturer states the absolute maximum permissible limit of TDS inside the boiler drum is 3,000 parts per million before scale starts to form.
Okay, let me do the math on this to make sure I'm following. We plug those numbers in. So it's 300 divided by the result of 3,000 minus 300.
Correct.
That means we divide 300 by 2,700. If you run that, it gives you exactly 1.11%. So 1.11% is the mathematical ideal. So in a perfect universe, your boiler only ever needs to purge 1.11% of its water volume to stay perfectly safe and scale-free.
That is the thermodynamic absolute.
Yeah.
But remember, our human operator, standing there with no sensor, relying on a schedule and a healthy fear of explosions.
Right, the guy who just wants to go home safe?
Yeah. They open that manual valve, maybe they leave it open for 60 seconds instead of 40 seconds, and over the course of the day, they end up blowing down 2% of the water instead of that ideal 1.11%.
I have to pause here because intuitively going from 1.11% to 2% sounds like absolutely nothing. I mean, it's an error of 0.89%.
It sounds tiny.
Right, in almost any other area of life, being less than 1% off is a massive success.
In a low-volume, low-energy system, it would be a rounding error. But in heavy industry, where you are dealing with continuous flow and extreme temperatures, that 0.89% difference is a structural, bleeding financial leak.
Wow.
To calculate the actual equivalent fuel wasted by that tiny fraction, we have to follow a very specific chain of physical conversions.
Walk us through that chain. How does a trickle of extra water turn into a mountain of wasted coal?
First, you have to calculate the physical mass of the excess water. You take that 0.89% excess volume and multiply it by the boiler's operating hours and the days it runs per year.
Okay, the Thermodynamic example breaks this down for a relatively small operation. They looked at a 2-ton per hour boiler running just 12 hours a day for 300 days a year.
A very modest setup.
Yeah, and even on that small scale, that tiny 0.89% overpurge equaled over 64,000 kilograms of excess water dumped straight to the sewer.
64 metric tons of water.
Unbelievable.
And crucially, that water is blistering hot. If the boiler is operating at a standard industrial pressure, say 10 kilograms per square centimeter, the thermal energy locked inside that water is enormous.
Because it's under pressure.
Right. The water temperature is sitting at roughly 180 degrees Celsius. You multiply the total mass of that dumped water by its specific heat energy. When you do that math, you are suddenly looking at tens of millions of wasted kilocalories of energy.
Wait, I need to make sure I understand how we translate tens of millions of kilocalories into a dollar amount for the factory owner. You have to figure out how much fuel it took to generate those kilocalories, right?
Precisely. Or rather, the calculation requires dividing those wasted kilocalories by the gross calorific value, or GCV, of the specific coal they are purchasing.
Let's define gross calorific value for the listener who isn't buying bulk coal. What does that term actually mean?
Gross calorific value is simply a measure of how much raw heat energy is released when you completely burn 1 kilogram of a specific fuel.
Ah, okay.
Different grades of coal burn hotter than others. In the source example, they audited a facility using coal with a GCV of 5,300 kilocalories per kilogram.
Okay, 5,300 kilocalories per kilogram. To put that in perspective for everyone, think about a standard, heavy bag of charcoal briquettes you might buy for a weekend barbecue.
Great comparison.
Every single kilogram of that coal has a specific energy output. What the math showed was that this tiny 0.89% manual overpurge equaled over 2,000 kilograms of equivalent fuel wasted in a single year.
Yes.
That is like taking hundreds of heavy bags of high-grade coal and throwing them directly into a dumpster year after year. And that is for a single small boiler.
Now take that foundational math and scale it up across an entire industrial sector. We reviewed real-world audit data published in the International Journal of Engineering Research and Applications.
The Agera study.
Right. They didn't just look at one boiler. They conducted a comprehensive audit across 10 different factories in the Surat Apparel Park in India.
The textile industry is a great baseline for this, right?
Yeah.
Because dyeing fabrics and processing textiles requires massive, continuous amounts of high-pressure steam.
The steam demand is relentless. The researchers proved that relying on these manual blowdown practices was resulting in up to 1.3% of those facilities' total daily coal consumption being completely wasted.
1.3% of the total daily coal.
Yes. In one of the larger plants they audited, that 1.3% equated to nearly 2 tons of coal wasted every single day.
Every single day.
Every day. 2 tons of fuel paid for, shoveled, burned, and dumped as hot wastewater.
When you lay the numbers out like that, it raises a really uncomfortable question about industrial incentives. If this waste is so massive and mathematically provable, who actually benefits from keeping this process manual and obscure? Because it certainly isn't the factory owner.
The Aegis strategy documents touch on this market dynamic perfectly. Obscurity always protects incumbents.
Protects incumbents. I like that phrasing.
It's true. The current wasteful state of affairs deeply benefits the coal and oil suppliers. They are happily securing purchase orders for that extra 1.3 to 5% of fuel month after month.
Wow, yeah.
The facility manager thinks they are just paying the necessary cost of doing business, but really they are subsidizing the fuel supplier.
And it doesn't stop with the fuel suppliers. The sources mentioned that the maintenance contractors benefit too, right?
Enormously. The companies that build the factories for expensive scale removal, acid washing, and heavy chemical water treatments thrive in an environment of imprecise manual control.
Because if the operator messes up,
Exactly. If the operator underpurges, the boiler scales up, and the maintenance contractor gets a lucrative descaling job. If the operator overpurges, the chemical treatments are flushed down the drain, and the contractor sells them more chemicals.
it's a win-win for everyone except the factory.
Right. The waste isn't a simple accident. It has calcified into a structural part of the industry's microeconomy.
So you have this deeply entrenched systemic leak. We've mathematically diagnosed the disease, but identifying the leak is the easy part. Now we have to talk about the physical cure.
The intervention.
Right. How do you actually stop a heavy, boiling, high-pressure leak in an active, dangerous industrial environment? I mean, you can't just slap a smart home water sensor on a 200-degree cast iron pipe.
Yeah.
This isn't a software bug you can patch from a laptop in a coffee shop.
No, absolutely not. The intervention requires an entirely different class of engineering. It requires heavy industry hardware. This brings us directly to the mechanical engineering principles behind the Aegis TDS loop automation strategy.
Okay, let's get into the Aegis system.
The founders of this strategy understood that you cannot solve a thermodynamic problem purely with software. You have to physically interface with the extreme environment. Their solution is a modular hardware retrofit kit specifically engineered to be installed on these 1 to 5 ton per hour MSME boilers.
The physical description of this hardware in the blueprints is striking. We are talking about a highly realistic mechanical intersection of two different eras of technology.
It's great visual.
On one hand, you have this pristine, hyper-machined, high-temperature conductivity and pH sensor probe. The documentation details its polycarbonate housing, a precisely milled aluminum collar, and a single tiny amber LED indicator light.
Very sleek.
It sounds like something out of an aerospace lab. And this futuristic sensor has to be physically threaded directly into a heavy-duty, oxidized cast iron pipe where the boiling wastewater flows.
That physical juxtaposition is the whole point. The sensor must survive contact with a brutal reality. It is enduring raw, fluctuating physical pressure and extreme heat 24 hours a day.
So it's tough.
Extremely tough. But while the ruggedized casing protects the hardware, the control logic inside that polycarbonate housing is what fundamentally changes the operation. This system replaces the manual valve with continuous, closed-loop, automated blowdown.
Let's define that control logic carefully. How exactly does this little sensor minimize the immense thermal waste we just calculated in the audit?
Well, it replaces human fear and guesswork with immutable thermodynamic truth. The electronic sensor sits directly in the flow of the boiler water and continuously monitors a metric called specific conductance in real time.
Wait, pause there. Specific conductance. For those of us who haven't taken a chemistry class in a while, how are they measuring dissolved rock using electrical conductance?
It relies on a beautiful quirk of physics. Pure distilled water is actually a fantastic electrical insulator. It does not conduct electricity well at all.
Really? Pure water doesn't conduct electricity?
Not effectively, no. It is the dissolved minerals, the calcium, the sodium, the magnesium salts that carry an electrical charge through the liquid.
Ah, so by sending a tiny, continuous electrical pulse through the water inside the pipe, the sensor is essentially measuring how easily that electricity travels from point A to point B.
That is the mechanism. The sensor reads the electrical current and knows that, roughly speaking, 1 microsiemens of specific conductance equates to about 0.55 to 0.90 parts per million of dissolved solids.
Okay, I follow.
So as the water gets more concentrated with minerals, the electrical conductivity rises proportionally.
So the system is essentially tasting the water chemically thousands of times a second to see exactly how salty it is.
And the telemetry is instant and constant. And this real-time data feed travels directly via a shielded cable into a programmable logic controller, or PLC. Yes. The PLC is the brain of the local operation, and it has one singular, uncompromising job: completely remove human discretion.
Because humans panic and humans guess.
Exactly. Human intervention in a continuous physical process introduces variance. You program the PLC with the exact mathematical permissible TDS set point we calculated earlier. Let's say the limit is exactly 3,500 parts per million.
Right.
The PLC continuously compares the live sensor data to that hard-coded set point.
And as long as the sensor reads 3,499 parts per million, the automated valve stays perfectly tightly shut. It retains 100% of that paid-for heat inside the boiler.
It waits for the exact microsecond the 3,500 threshold is breached. When the water finally crosses that line, the PLC sends an electrical signal to a heavy, motorized actuator box bolted onto the valve.
And then what happens?
There is a rigid mechanical precision to this actuation. The motor physically turns the valve stem exactly 90 degrees with unyielding authority. The valve opens, purges the absolute mathematical minimum amount of boiling water necessary to drop the total boiler concentration back below the safety threshold, and then the motor snaps the valve shut again.
Wow. No guessing. No operator opening it for an extra 30 seconds just to feel safe. Just pure mathematical control of the physical environment.
The thermal leak is instantly plugged. But the Aegis system takes the strategy a step further, and this is where we see the leap from traditional automation into modern edge computing.
Yes, this part of the blueprint completely shifted my perspective on industrial tech. The system isn't just a dumb valve blindly reacting to a threshold. It is edge computed.
Right.
The Aegis strategy involves integrating a localized artificial intelligence, a specialized large language model, to analyze the constant stream of sensor telemetry over time.
Which is a fascinating application. We usually think of LLMs as text generators, writing emails or summarizing articles. How do you apply an LLM to boiling water?
Right. I had the exact same question when reading the sources. How does an AI read boiler telemetry? The blueprint explains that the system tokenizes the time series data.
Tokenizes the data.
Yeah, it treats the fluctuations in electrical conductance over hours and days as a sequence of patterns. The AI isn't just reacting to the 3,500 ppm limit. It is actively looking at the slope of the curve. It watches how fast the scale is accumulating.
It is looking for the derivative of the data. It is measuring the rate of change.
And because it understands the baseline rate of change, it can output predictive maintenance alerts.
Which is huge for facility managers.
Exactly. If the municipal city water supply suddenly changes, maybe there was heavy rain and the incoming water is suddenly much harder, the operator wouldn't notice until the scale started forming.
They'd be totally blind to it.
But the local AI sees the microscopic shift in the accumulation speed instantly. It pings the facility manager's dashboard and says, hey, your incoming feed water quality just degraded by 12%. Check your water softeners today before it becomes a crisis tomorrow.
That capability is the true power of bridging physical hardware with digital intelligence. You are moving a factory from a reactive posture to a predictive posture.
A total paradigm shift.
It really is. But I want to pivot here because the sources dedicate a significant amount of ink to something beyond the math and the hardware.
Oh, the mindset stuff.
Yes. To execute a mechanical intervention like this, to ask an engineer to walk into a loud, dangerous 200-degree boiler room and physically alter the pressure boundary of a steam boiler requires a very specific psychological approach.
It requires an entire philosophy. The operational blueprints refer to this specific persona as the quiet architect.
The quiet architect. It is a striking term for an engineer. The foundational philosophy laid out in the text is a concept they call restorative engineering, and their core mantra is, technology doesn't replace people, it restores them.
I want to dig into that because disruption is the favorite buzzword of the tech industry. Every startup wants to disrupt an industry.
The blueprint actively pushes back against that mindset. In consumer software, breaking things and moving fast is fine. But in a high-pressure boiler room, disruption means a steam explosion.
Literally.
Literally. Disruption means a catastrophic loss of heavy infrastructure and, more importantly, a potential loss of life. The mindset required to build and deploy this specific hardware retrofit is one of extreme functional restraint.
The source document shared a deeply personal anecdote from the founder that really anchored this concept for me.
The explosives story.
Yeah. The engineer writing the blueprint was talking about a previous project, watching factory workers manually handling explosives, literally handling live materials to assemble detonators. He described watching these workers perform their tasks as if they were holding their breath. The tension in the room was palpable.
Because a single millimeter of human error meant a fatal detonation.
Exactly. So his engineering team didn't try to build a flashy app to optimize the schedule. They built a physical intervention.
A cobot, right.
Right. They engineered a 6-axis collaborative robotic arm, a cobot heavily integrated with AI and vision systems to physically handle the hazardous material instead of the humans.
Incredible.
The robot didn't take the workers' jobs, it took the physical risk away from them. And the founder wrote that the true metric of success for that project wasn't the company's valuation or a headline in a tech blog. The only metric that mattered was a worker sending a message at the end of the shift saying, "I reached home safe tonight."
That anecdote perfectly encapsulates restorative engineering. You are using advanced technology to restore peace of mind to the human operator, and you apply that exact same psychological framework to the boiler room.
Removing the fear.
Exactly. The Aegis loop is ultimately about securing the perimeter of safety. It removes the fear of a boiler explosion from the operator's daily life and simultaneously prevents severe scaling. It is not about being flashy. It is about total accountability.
And you see that demand for accountability perfectly mirrored in the physical design aesthetics of the Aegis hardware. The blueprints specifically cite the design principles of Dieter Rams, the famous industrial designer.
Ah, less but better.
Yes, less but better. The documents explicitly reject chaotic motion, unnecessary LEDs, and what they call ornamental futurism. The hardware must project calm, undeniable authority.
Form following function in an extreme environment.
That's why they focus so heavily on the visual contrast. I mentioned it earlier, but the blueprint demands the juxtaposition of the rough, pitted, heat-stressed surface of the heavy cast iron pipe against the flawless, light-absorbing matte finish of the modern actuator housing. They call it material honesty.
That design language is not just about looking good in a brochure. It is a communication tool directed at the pragmatic, deeply skeptical factory manager.
Right, they aren't easily impressed.
Not at all. A facility manager who spends their life keeping heavy machinery running inherently distrusts glossy, slick marketing. They understand raw physical risk. When they look at a piece of equipment, they need to know it won't fail when the temperature spikes.
They need to trust it instinctively.
Yes. When they see a ruggedized, heat-shielded product that refuses to be complicated, that does exactly one highly specific thing perfectly, it commands respect through austere technical exactness.
Well said.
As the architect notes in the text, a brilliant AI prompt or a clever LLM integration is completely useless without a rugged physical product behind it. In heavy industry, what survives contact with reality matters far more than what sounds impressive in a boardroom pitch.
Which leads to my absolute favorite line in the entire stack of sources.
Let me guess, the printer line.
Yes. The founder is writing about bridging edge, AI, thermodynamics, and precision robotics, doing this profound, life-saving restorative engineering,
Yeah.
and then adds, "My mother still thinks I just fix printers. She's not entirely wrong."
It is a brilliant moment of self-awareness.
It grounds the entire philosophy. It's that cultural humility. You don't take yourself too seriously, even when the work is critical. You are essentially just fixing a very large, very dangerous boiling water printer.
It is a vital emotional calibration for an engineering team. You need that grounded reality because ultimately we have to face the business reality.
The financials.
Right. Even the most beautiful, restorative, Dieter Rams-inspired engineering will utterly fail in the competitive industrial market if the economics don't make sense to the person signing the checks. You have to prove the financial value to a highly skeptical buyer.
Right. The plant manager might appreciate the design, but the CFO needs to know how it impacts the bottom line. How do you pay for it? Let's transition into the economics of the edge. How does a facility manager actually calculate the financial payback period for this kind of hardware retrofit?
We can look at the standard capital expenditure purchasing model first, using the specific Steamline Nanotron automation example provided in the texts. Let's say the factory decides to buy the automated hardware system outright. The equipment costs 155,000 rupees.
Okay, 155,000 rupees upfront capital cost.
Now we factor in the savings from the audit. Because the sensor and PLC completely eliminate that 0.89% human over-purging, the facility calculates the exact daily reduction in wasted coal, the reduction in dumped city makeup water, and the reduction in wasted chemical treatments.
All those savings add up.
They do. They determine that the system saves them exactly 867 rupees every single day.
Let me run that simple math. So 155,000 rupees total cost divided by 867 rupees saved per day. That gives you a precise payback period of exactly 178 days, or roughly 6.2 months.
A 6.2-month payback period.
That is incredibly fast for industrial equipment. In less than 7 months, the machine has entirely paid for itself, and from that point on, every single day it operates, it is just generating 867 rupees of pure found profit through efficiency.
That is the traditional hardware sales model, and it is a strong value proposition. But the Aegis strategy documents outline an asymmetric advantage. They introduce a brilliant, aggressive monetization model that flips the script: do not sell the hardware.
Well, if the payback period is that good, why wouldn't you just sell thousands of these boxes and take the cash? What do they do instead?
They execute an energy-as-a-service contract.
Energy as a service.
Right. The Aegis startup walks into the textile factory and offers to install the entire TDS Loop hardware system, complete with the AI telemetry, at zero upfront capital cost to the facility manager.
Zero upfront. For a highly engineered hardware retrofit, that seems like a massive capital risk for a startup to absorb. They're essentially giving away expensive machinery.
It appears to be a risk if you think like a traditional hardware vendor, but the startup isn't selling metal and plastic, they're capturing the control point. In exchange for the free hardware and installation, the startup secures a binding contract to take 30% of the daily coal and water savings over a 36-month term.
Oh, wow. Okay, I need to make sure I grasp the sheer scale of this pivot. Let me try another analogy. This ES model sounds somewhat similar to the solar industry, right?
Very similar.
It's like a company coming to your house, installing $30,000 worth of solar panels on your roof for absolutely free. But the catch is, they get to keep 30% of the money you save on your monthly electric bill for the next 10 years.
That is the exact financial mechanism, translated to industrial thermodynamics. Instead of selling a physical product once for a fixed price of 155,000 rupees, they capture the data stream. They use the hardware as a Trojan horse to turn a physical thermodynamic leak into a recurring revenue stream. The value isn't in the polycarbonate sensor, the value is in the recovered enthalpy.
That is a brilliant business model, but it relies entirely on trust. How do you objectively prove to the factory owner who is already skeptical exactly how much coal you save them every day? You can't just send them an invoice saying, "Trust us, we saved you a ton of coal."
And that is exactly where the AI dashboard and the edge computing justify their existence. The sensor provides unquestionable, immutable proof of the thermal delta.
The receipts, basically.
Exactly. The dashboard shows the factory manager exactly what the specific conductance was at every second of the day, exactly when the valve opened, and calculates the exact mass of water retained compared to the old audited manual baseline.
It makes the invisible totally legible.
The sensor loop dictates the energy efficiency baseline. The entity controlling that sensor and interpreting that data effectively owns the value created by the efficiency.
So step back and look at what this means for the facility. It is an irresistible offer. The plant manager gets a vastly safer boiler, totally eliminating the explosion risk from scaling.
Yep, huge safety win.
They get an AI system predicting their water quality. They spend zero upfront capital expenditure, which keeps the CFO happy. And from day one, they immediately pocket 70% of the coal savings while the startup takes their 30% cut. It's a total no-brainer.
It is a perfectly aligned incentive structure, and the engineering handbooks highlight that it doesn't even stop at just controlling the blowdown valve. The Violi documentation and the textile audits point out that once you have precisely automated the blowdown, facility managers can further stack these financial savings through a mechanical process called heat recovery.
Well, I wanted to ask about this because even with the Aegis system running perfectly, hitting that ideal 1.01%, well, that 1.1% of water you have to purge to remove the minerals, is still sitting at 200 degrees Celsius. You are purging less water, but the water you do purge is still dumping valuable heat into the sewer.
You are still bleeding enthalpy. But because the automated valve provides a highly consistent, predictable flow of wastewater, a smart engineering operation will capture that heat before it hits the drain. They take the automated blowdown water and pipe it through a vessel called a flash tank system.
The sources mentioned flash tanks. Walk me through the physics of what happens inside that tank.
Well, the blowdown water is incredibly hot, but it remains liquid inside the boiler because it is under immense pressure. When the automated valve opens, it routes that 200-degree high-pressure water into the flash tank, which is maintained at a much lower pressure.
So the pressure drops suddenly.
Right. Because the pressure suddenly drops, the thermodynamic equilibrium shifts. A significant portion of that liquid water instantly flashes or explosively boils into low-pressure steam.
It turns back into clean steam. And what do they do with that newly created low-pressure steam?
They capture it and pipe it directly back into the facility's decarrators.
Okay, pause. Decarrators. That's a heavy piece of jargon. For the listener who isn't standing in a boiler room right now, what is that machine and why does it need the steam we just recovered?
A decarrator is a specialized feedwater tank. Its job is to heat the incoming cold makeup water from the city to drive out dissolved oxygen and carbon dioxide before the water enters the main boiler.
Why do you need to drive out oxygen?
If you pump cold, oxygen-rich water into a steel boiler, the oxygen will aggressively attack the steel and cause severe pitting corrosion. So you have to heat the feed water to boil the oxygen out.
And instead of burning fresh coal to heat the deaerator, you use the free recycled steam from the flash tank. That is incredibly elegant. But wait, flashing the steam only captures a portion of the heat. What about the highly concentrated, dirty hot water that doesn't flash into steam and stays liquid in the tank?
You extract the heat from that liquid as well. You run that remaining hot wastewater through a heavy-duty heat exchanger. A heat exchanger is essentially two pipes running closely alongside each other, allowing heat to pass between them without the fluids mixing.
Okay.
You pass your cold, incoming city makeup water through one side of the exchanger and the nearly boiling blowdown wastewater through the other side.
So the dirty wastewater transfers its heat into the clean makeup water, preheating it before it ever enters the system.
Precisely. The blowdown wastewater is cooled down to a safe temperature before it finally hits the municipal sewer, and the incoming clean water is preheated by 40 or 50 degrees.
Thus requiring even less coal to bring that fresh water up to the final boiling temperature inside the main furnace.
It is a compounding loop of efficiency. Between the precision of the Aegis automatic control valve, the recovery of steam in the flash tank, and the thermal transfer in the heat exchanger, a facility can ultimately recover up to 80 to 85% of the thermal energy that was previously just being dumped down the drain by a manual operator.
It is an incredible cascade of engineering solutions. But this raises a really nagging question for me. If this is so lucrative, if the math is so clearly proven in the audits, and if the ES model removes all the financial risk, why isn't every single factory on Earth already doing this? Why is this still a hidden problem?
That brings us full circle back to the founder-grade market lens outlined in the Aegis strategy. We said it earlier, obscurity protects incumbents. But it is more than just the fuel suppliers maintaining the status quo. It is an issue of corporate visibility.
What do you mean by corporate visibility?
Well, when an industrial process is noisy, physically dangerous, located in a dark boiler house away from the main office, and poorly understood by upper management, the immense waste is just accepted as a fixed operating cost. The CFOs and plant managers who make the budget decisions are completely disconnected from the physical reality of the manual blowdown valve.
The actual bottleneck isn't the technology, and it isn't even the cost of the hardware. The bottleneck is the lack of real-time thermodynamic feedback reaching the people who actually write the checks. The executives only see the total coal bill at the end of the month. They don't see the 0.89% leak happening second by second.
And the winner in this scenario, the entity that stands to profit the most, is the early recognizer, the startup or the sharp facility operator who realizes that taking this obscure, messy physical process and making it mathematically legible creates an asymmetric competitive advantage.
They see what others miss.
Exactly. By deploying the sensor, they stop burning money and start capturing it. They leverage extreme precision to extract value from a system everyone else has written off as a necessary evil.
Okay, let's take a breath and summarize this incredible journey we've been on. We started with the sheer brute force physics of boiling water and the hidden dangers of microscopic scale, how a single millimeter of rock can lead to a catastrophic explosion.
A literal bomb.
Right. We walked through the rigid math of the 48-hour audit, calculating exactly how a tiny 0.89% manual overpurge turns into literal tons of wasted coal. We explored the mechanical elegance of the Aegis TDS loop, relying on real-time specific conductance to remove human fear and guesswork from the equation.
Bringing digital truth to physical hardware.
Yes. We delved into the quiet architect mindset, the philosophy of restorative engineering that uses AI and precision mechanics not to disrupt, but to secure safety and protect human workers. And finally, we unpacked the genius energy-as-a-service financial model coupled with heat recovery that turns a leaky, rusty pipe into a highly lucrative recurring revenue stream.
It truly is a masterclass in seeing the structural opportunity hidden within the industrial noise. The Aegis blueprint proves that technological innovation isn't always about creating entirely new paradigms or building flashy consumer apps. Often the most impactful innovation is simply applying extreme precision, rugged hardware, and accountability to the overlooked messy realities of the physical world.
And that leaves us with a final thought for you to mull over as we wrap up. The Aegis strategy proves that the biggest, most lucrative opportunities in artificial intelligence and automation today might not be in generating text, writing code, or creating images on a screen. The real trillion-dollar opportunities might be hiding out of sight in dark, noisy boiler rooms wrapped around a rusty cast iron pipe. What other invisible physical processes in your own industry are still running on human guesswork and outdated shift schedules, just waiting for someone to measure the truth and capture the waste? Thank you for joining us on this deep dive. Stay insanely curious.